I'm glad to have you back on the channel. It's been a while since our last upload, mainly due to internet issues and the difficult situation caused by recent conflicts. But we're finally back, and I truly appreciate your patience and support during this time. Please don't forget to like, comment, and subscribe. Your support really motivates us to continue creating high-quality content. And if you have any questions, feel free to drop them in the comments. I'll make sure to answer them as soon as possible. Now, let's continue where we left off. We've completed the simulation, and it's time to start reviewing the results. Inside ANSYS Fluent, in the outline view, expand the Results section and click on Graphics. Then, choose Contours from the list. In the Contours panel, under Contours of, select Velocity. And for the variable below that, choose Velocity Magnitude. Make sure the filled box is ticked, but do not select any surfaces. Then, click Display to generate the plot. Since we're working in a 2D simulation, Fluent will automatically show the contour on all cells, so there's no need to manually pick a surface. To zoom in on the hub, click and drag the middle mouse button from the top left to the bottom right. This zooms in. Doing it in the opposite direction, bottom right to top left, will zoom out. And if you ever get lost in the zoom, just click Fit to Window to reset the view. As you can see, the velocity contours now display clearly on the screen. If we hadn't used the moving reference frame (MRF) technique for the rotating parts, this visualization would have appeared much more symmetrical, especially between the top and bottom sections. But thanks to MRF, we now see a more realistic and accurate flow pattern around the blades. This confirms that the rotation effect is properly captured in the simulation, and we're observing the expected asymmetry caused by the turbine's motion. Now, it's a good time to save your project. Go to File greater than Save Project to make sure all your progress is stored. Once saved, go ahead and close Fluent and return to the main ANSYS Workbench window. Now, let's move on to a different and more dynamic simulation approach, using sliding meshes. There are situations where the MRF method we used earlier might be too much of an oversimplification. Why? Because in MRF, we only simulate one static position of the rotating hub relative to the incoming wind. But in reality, as each blade rotates, it interacts with vortices and flow disturbances left behind by other blades that have just passed. MRF can't fully capture these time-dependent effects. So in this method, we'll take it to the next level by actually moving all the components in the simulation using Fluent's sliding mesh technique. This allows us to simulate the true, continuous rotation of the wind turbine and solve the problem in a transient or time-dependent manner. Let's jump into the setup and see how we can implement this powerful method in ANSYS Fluent. Let's now get started with setting up the sliding mesh simulation in ANSYS Fluent. On the Workbench project page, simply right-click on the small arrow icon at the top of the existing Fluent system and select Duplicate. This creates an exact copy of the mesh and model. Now, rename this new system to something clear, like Sliding Mesh Model. Next, we're going to reuse the results from our previous MRF simulation. To do that, drag a connection line from the results cell of the MRF system, A3, to the results cell of the new system, B3. Why do we do this? Well, this allows us to use the converged steady-state solution from the MRF method as a starting point for our new transient sliding mesh computation, making the process faster and more stable. Once that's done, double-click on the new solution cell B3 to launch Fluent, and we're ready to dive into the next phase of the simulation. When the new Fluent session opens for the sliding mesh model, you'll notice that all the model setup values, including boundary conditions, material properties, and more, are automatically carried over from the MRF setup. It's a good idea to take a moment to look through the boundary conditions or even plot the velocity contours to confirm that everything is still intact before moving forward. Now, in the following steps, we'll begin converting this model into a true sliding mesh case, which involves actual motion of the computational zones over time. It's important to understand the key difference here. The hub's motion is relatively easy to define. It rotates around a fixed axis, but the blades are trickier. That's because each blade not only rotates about its own axis, but that axis itself is moving along the hub's rotation. A combined motion of translation and rotation. To handle this complexity, we've provided a user-defined function, or UDF, specifically tailored for this simulation. This UDF will apply the correct combined motion to each blade, allowing for an accurate and realistic sliding mesh simulation. Let's continue setting up the simulation using the sliding mesh approach. First, under Problem Setup, General, Solver, make sure to select Transient as the solver type. Since this model involves actual movement over time, a steady-state solution isn't enough. We need a time-dependent solver to capture the dynamics. Next, it's time to read in the user-defined function, or UDF, that we'll use to apply blade motion. Follow these steps. Copy the file named WS5_UDF for motion.ce into the user files folder inside your project directory. Then, in Fluent, go to Define, User-Defined, Functions, Interpreted. Click Browse and select the .c file from your user files folder. Make sure to tick both Display Assembly Listing and Contributed CPP. This will show you what's happening under the hood. Finally, click Interpret. You'll see a stream of about 700 lines of machine code appear in the TUI window. This indicates that the UDF has been read successfully, and there are no syntax errors. Now, a quick note about UDFs. There are two main ways to bring them into FLUENT, interpreted and compiled. We're using the interpreted method here because this UDF is fairly simple, quick to execute, and doesn't require any external compilers or extra software. Don't worry, we'll cover UDFs in more detail in a separate lecture. But for now, this method works perfectly for our needs. Now let's activate the sliding mesh model in our simulation. Go to Problem Setup, Cell Zone Conditions, and select Fluid Rotating Core, then click Edit. In the Reference Frame tab, click on Copy to Mesh Motion. This action switches the motion type from frame motion, which was used in the moving reference frame approach, to mesh motion, which is required for a sliding mesh simulation. Now, move to the Mesh Motion tab. Here you'll notice that the rotation speed has been automatically transferred from the frame motion settings to mesh motion. That's exactly what we want. No need to manually re-enter it. Click OK to apply these settings and complete the conversion of this zone to a sliding mesh configuration. This step is crucial because it tells Fluent that the mesh itself will physically rotate, which allows for a fully dynamic simulation of the turbine. Now, the setup will be slightly different for the 4 blades when using the sliding mesh method. Start by selecting Fluid Blade XNEG and click Edit. Here's the important part. The motion for these blades will be manually defined by the UDF, so we don't need to copy the motion from the previous MRF settings. This is because the user-defined function already contains the correct axis position and rotation speed. Now, uncheck Frame Motion. Enable Mesh Motion. Then go to the Mesh Motion tab. In the UDF field, select Motion X negative. Be very careful to choose the correct UDF and ensure that only Mesh Motion is selected, not both. Then click OK. Now repeat the same steps for the remaining blade zones. Finally, double-check each zone to verify the correct UDF has been applied. This is crucial to ensure the simulation runs properly, as each blade follows a unique motion path defined in the UDF. That brings us to the end of this part of the tutorial. In this section, we focused on setting up the sliding mesh method for simulating the rotation of the wind turbine blades in a transient manner. We applied the user-defined functions, UDFs, to define the individual motion of each blade and carefully assigned the correct motion profiles to all blade zones. This method allows us to capture time-dependent interactions between rotating blades and the surrounding flow, providing a more realistic and detailed analysis compared to the steady-state MRF method. We hope you found this part helpful. Don't forget to like, comment, and subscribe to support the channel. Your feedback really motivates us to keep creating more valuable content for mechanical engineers like you. Stay tuned for the next part, where we continue this exciting project in ANSYS Fluent.